Introduction to RFC 8017. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into RFC 8017, which defines PKCS number 1, version 2.2. This is the RSA cryptography specification standard, and it is one of the most important documents in modern cryptography. RFC 8017 is an update that obsoletes the previous RFC 3447, bringing clarifications and improvements to the RSA cryptographic system that we use every single day. RSA, named after its inventors Rivest, Shamir, and Adelman, has been the workhorse of public key cryptography since 1977. This RFC standardizes how RSA operations are performed, including key generation, encryption, decryption, signing, and signature verification. It is used in TLS certificates, SSH authentication, email encryption with PGP, code signing, and countless other security applications. The RFC defines two main encryption schemes: RSAES-OAEP, which is the modern recommended approach using optimal asymmetric encryption padding, and RSAES-PKCS 1v1_5, which is the legacy scheme still widely deployed. For digital signatures, it specifies RSASSA-PSS, which uses probabilistic signature scheme, and RSASSA-PKCS 1v1_5, which is the traditional deterministic signature scheme. Understanding RFC 8017 is crucial because it forms the mathematical and cryptographic foundation for secure communications across the Internet. Every time you connect to a website with HTTPS, authenticate to a server with SSH, or verify a software update, there is a good chance RSA cryptography based on this specification is protecting you. The RFC provides not just the algorithms but also guidance on security considerations, key sizes, and proper implementation practices that prevent common cryptographic mistakes. RSA key structure and components. Let's start by understanding what an RSA key actually contains. An RSA key pair consists of a public key and a private key, each with specific mathematical components that work together to enable encryption and digital signatures. The public key contains just two components, N and E. The value N is called the modulus, and it is a large number which is the product of two secret prime numbers P and Q. Typically, N is 2048 bits or 4096 bits in length. The value E is called the public exponent, and it is usually a small number, such as 65537, which is written as beginning with 0x01 and ending with 01 in hexadecimal. The reason 65537 is so popular is that only two of its bits are set to 1, which makes the exponentiation operation faster while still maintaining security. The private key contains significantly more information. It always includes the modulus N and the private exponent D. The private exponent D is the mathematical inverse of E modulo phi of N, where phi of N equals P minus 1 times Q minus 1. This relationship is what makes RSA work mathematically. Additionally, the private key typically includes the two prime factors P and Q that were used to generate N, plus 3 additional values for optimization. These optimization values are dp, which is d mod p minus 1, dq, which is d mod p minus 1, and qinv, which is the inverse of q mod page. These values enable something called the Chinese remainder theorem optimization, which makes private key operations about 4 times faster. Without these pre-computed values, decryption and signing would be significantly slower, which matters when you are processing thousands of TLS handshakes per second on a busy web server. The security of RSA depends entirely on the factorization problem. Given N, it should be computationally infeasible to factor it back into P and Q. If an attacker could factor N, they could compute D from E and phi of N, completely compromising the private key. This is why we use such large key sizes. Currently, 2048 bits is considered the minimum for security through 2030, while 4096-bit keys provide an additional security margin for highly sensitive applications. RSA mathematical primitives. Before we can encrypt or sign data with RSA, we need to understand the fundamental mathematical operations that RFC 8017 defines. These are called the RSA primitives, and they are the low-level building blocks that the encryption and signature schemes are built upon. The first primitive is RSAEP, which stands for RSA encryption primitive. This operation takes a message representative M, which must be an integer between 0 and n-1, and raises it to the power of the public exponent e, then takes the result modulo n. Mathematically, ciphertext C equals m to the power e mod n. This is a trapdoor one-way function, meaning it is easy to compute in the forward direction but hard to reverse without the private key. The second primitive is RSADP, the RSA decryption primitive. This takes a ciphertext representative C and raises it to the power of the private exponent d, then takes the result modulo n. So message m equals C to the power d mod n. This inverts the encryption primitive. The beautiful mathematical property of RSA is that raising to e then d, or raising to d then e, both get you back to the original value modulo n. For digital signatures, we have RSASSP1, the RSA signature primitive. Despite the name, it actually uses the same mathematics as RSADP. You take a message representative m and compute signature s equals m to the power d mod n using the private key. This is why signature generation requires the private key and is computationally expensive. Finally, there is RSAVP1, the RSA verification primitive, which uses the same math as RSAEP. You take a signature s and compute m equals s to the power e mod n using the public key. This is fast because e is small, and anyone with the public key can verify signatures. The verification checks that the recovered message representative matches the expected value derived from the actual message. These primitives operate on integers, not arbitrary data. This is why encryption and signature schemes need padding mechanisms to convert variable-length messages into properly formatted integer representatives in the range 0 to n-1. The padding is also crucial for security, as raw RSA primitives without padding have numerous vulnerabilities including malleability attacks and chosen ciphertext attacks. RSAES-OAEP encryption scheme. RSAES-OAEP is the modern, recommended encryption scheme defined in RFC 8017. OAEP stands for Optimal Asymmetric Encryption Padding, and it was designed by Bellare and Rogaway to provide provable security against chosen ciphertext attacks. This is the scheme you should use for new applications that need RSA encryption. The OAEP padding mechanism is quite sophisticated. It starts with your actual message M that you want to encrypt. First, the scheme generates a random seed, typically using a cryptographic random number generator. This seed is crucial for semantic security, meaning that encrypting the same message twice produces different ciphertexts, which prevents attackers from recognizing when the same data is encrypted multiple times. The padding process uses a mask generation function, typically MGF1, based on a hash function like SHA-256. The seed is used to generate a mask that gets XORD with the padded message. Then the masked message is used to generate another mask that gets XORD with the seed. This two-step masking process creates a data block that has properties that make it secure against adaptive chosen ciphertext attacks. An important parameter in OAEP is the label L, which is an optional value that can be associated with the message. Most implementations use an empty string for L. The label gets hashed and included in the padding structure. If you encrypt with one label and try to decrypt with a different label, the decryption will fail. This can be useful in protocols where you want to bind the encryption to a specific context. The maximum message length that RSAES-OAEP can encrypt depends on the key size and hash function. For a 2048-bit key using SHA-256, you can encrypt at most 190 bytes of data. This is calculated as k-2 times h-len-2, where k is the key length in bytes, 256 for 2048 bits, and h-len is the hash output length, 32 bytes for SHA-256. If you need to encrypt larger messages, you should use hybrid encryption where you generate a random symmetric key, encrypt your data with AES or SHA-20, then encrypt just the symmetric key with RSA-OAEP. RSAES-OAEP encryption process. Let's walk through the actual encryption process for RSAES-OAEP step by step. Understanding this process helps you implement it correctly and debug issues when they arise in real systems. Step 1 is length checking. You verify that the message length is at most k-2 h-len-2 bytes, where k is the length of the modulus in bytes, and h-len is the hash output length. For example, with a 2048-bit key and SHA-256, k is 256 bytes, and h-len is 32 bytes, so the maximum message is 190 bytes. If the message is too long, the encryption must fail immediately. Step 2 is EME-OAEP encoding. This is where the sophisticated padding happens. First, you hash the label parameter L using your chosen hash function to get L hash. Then you create a padding string PS consisting of 0 bytes, with length k-m-len-2 h-len-2. You concatenate L hash, PS, a single 0x01 byte, and the message M to form a data block DB. Next, you generate a random seed of length h-len bytes. Step 3 continues the EME-OAEP encoding with the masking operations. You apply MGF1 to the seed to generate a masked DB mask of length letter k-h-len-1. XOR the data block DB with DB mask to get masked DB. Then apply MGF1 to masked DB to generate a masked seed mask of length h-len. XOR the seed with seed mask to get masked seed. Finally, concatenate a single 0x00 byte, masked seed, and masked DB to form the encoded message EM of length letter K bytes. Step 4 is the RSA encryption. Convert the encoded message EM to an integer M, using the OS2IP operation defined in the RFC, which interprets the octet string as a big Indian integer. Apply the RSAEP encryption primitive with the recipient's public key to compute C equals M to the power E mod N. Convert the integer C back to an octet string C of length K, using I2OSP, which converts an integer to a big Indian octet string. This octet string C is your final ciphertext. The decryption process essentially reverses these steps. After applying the RSADP primitive with the private key, you unmask the seed and data block, verify that the structure is correct including the L hash and the 0x01 separator byte, and extract the original message M if any check fails during decryption. The operation must fail without revealing which specific check failed, to prevent chosen ciphertext attacks based on timing or error messages. RSAES-PKCS 1B15 Legacy Encryption. RSAES-PKCS 1 version 1.5 is the original RSA encryption scheme from the PKCS No. 1 standard. While RFC 8017 still includes this scheme for backwards compatibility, it is considered legacy, and new applications should use RSAES-OAEP instead. However, understanding PKCS 1 version 1.5 is important because it is still widely deployed in existing systems. The padding in PKCS 1 Volt 1.5 is much simpler than OAEP, which is actually part of the problem from a security perspective. The encrypted message EM has the structure 0x00, 0x02, followed by at least 8 random non-zero padding bytes, then a 0x00 byte separator, then the actual message M. The total length is k bytes, where k is the modulus length in octets. The random padding bytes must be non-zero and are typically generated using a cryptographic random number generator. The requirement for at least 8 random bytes means the maximum message length is k-11 bytes. For a 2048-bit key, that's 245 bytes maximum. This is more than OAEP allows, but the simpler padding structure makes it less secure. The main vulnerability in PKCS 1v15 is its susceptibility to adaptive chosen ciphertext attacks, particularly the Bleikenbacher attack discovered in 1998. This attack exploits the padding validation during decryption. When a server decrypts a ciphertext and checks if the padding is valid, even tiny differences in error handling or timing can leak information that allows an attacker to decrypt messages or forge signatures. Despite these vulnerabilities, PKCS 1v1_5 is still used in many protocols including TLS 1.2 for the RSA key exchange. Modern implementations use careful countermeasures to prevent timing attacks, such as performing the same number of operations regardless of whether the padding is valid, and returning generic error messages that do not reveal which check failed. If you must use PKCS 1v1_5 for compatibility, ensure your implementation includes these protections and consider upgrading to OAEP or using elliptic curve cryptography instead. RSASSA-PSS Signature Scheme. RSASSA-PSS is the modern probabilistic signature scheme specified in RFC 8017. PSS stands for Probabilistic Signature Scheme, and like OAEP for encryption, it was designed by Bellare and Rogaway with provable security properties. This is the recommended signature scheme for new applications. The key innovation in PSS is that it is randomized. Each time you sign the same message, you get a different signature. This randomization comes from a random salt value that is generated during signing. The salt is typically 32 bytes for SHA-256. This randomization provides security benefits, including resistance to certain types of attacks that affect deterministic signature schemes. PSS uses a sophisticated encoding mechanism called EMSA-PSS, which stands for Encoding Method for Signature with Appendix, PSS variant. The encoding process starts by hashing your message M using your chosen hash function to get a message hash, M hash, of length h len bytes. Then, you generate a random salt of length s len bytes, typically equal to h len. The encoding continues by building a structure. This structure consists of 80x00 bytes, followed by M hash, and then by the salt. You then hash this entire structure to get H. Next, you create a data block, dB. This block consists of a padding string, PS, of 0 bytes, followed by a 0x01 byte, and then the salt. The length of PS is calculated to ensure the total encoded message is the correct size. The masking step applies MGF1 to H to generate dB mask, which is XOR'd with dB to produce masked dB for encoded messages that are not a multiple of 8 bits. The leftmost bits of masked dB are set to 0. Finally, you concatenate masked dB, H, and a trailer byte 0xBC to form the encoded message EM, which then gets signed using the RSASP1 primitive with the private key. Signature verification reverses this process. After applying RSAVP1 with the public key to recover the encoded message, you unmask the dB, extract the salt, recompute H from the message hash in salt, and verify that it matches the H in the signature. If any check fails, the signature is invalid. The randomization means you cannot simply compare signatures for equality. You must perform the full verification algorithm. RSASSA-PSS signature generation. Let's walk through the detailed process of generating an RSASSA-PSS signature. This will help you understand exactly what happens when you call a signing function in a cryptographic library. Step 1 is to apply the EMSA-PSS encoding operation to the message M. This starts by hashing the message with your chosen hash function, for example SHA-256, to get M hash, which is 32 bytes. Generate a random salt value, typically also 32 bytes for SHA-256, using a cryptographically secure random number generator. The salt length can be up to HLN bytes, and longer salts provide better security, but result in larger encoded messages. Step 2 constructs the M' structure. This structure consists of 8 0 bytes, followed by M hash, then followed by salt. You then hash this entire M' structure. The result is H, which is 32 bytes for SHA-256. The 8 0 bytes at the beginning are a security measure that ensures the hash input is structured properly. Step 3 creates the data block DB. Start with a padding string PS consisting of 0 bytes. The length of PS is mlen-slen-hlen-2 bytes, where mlen is the intended length of the encoded message, typically the same as the modulus length -1. After PS comes a single 0x01 byte, then the salt. This creates a data block DB of length mlen-hlen-1 byte. Step 4 performs the masking operation. Apply MGF1 with your hash function to H to generate DB mask of the same length as DB_XOR with DB mask to produce masked DB if M bits, which is the bit length of the modulus -1, is not a multiple of 8. Set the leftmost 8 mlen-m bits of the leftmost octet in masked DB to 0. This ensures the encoded message is the correct bit length. Step 5 assembles the encoded message EM by concatenating masked DB, H, and the constant byte 0xBC. This EM is now ready for signing. Convert EM to an integer M using OS2IP. Apply the RSASSP1 signing primitive to compute S equals M to the power D mod N using your private key. Convert S back to an octet string S of length K bytes using I2OSP. This octet string S is your RSASSA-PSS signature. RSASSA-PKCS1 version 1.5 signature scheme. RSASSA-PKCS1 version 1.5 is the traditional deterministic signature scheme that has been used since the original PKCS number 1 standard. Unlike PSS, this scheme is deterministic, meaning signing the same message with the same key always produces the same signature. While RFC 8017 still specifies this scheme, new applications should prefer PSS for its stronger security properties. The encoding mechanism for PKCS1 version 1.5 signatures is called EMSA-PKCS1 version 1.5. It is much simpler than PSS encoding. First, you hash your message M using your chosen hash function to get a digest H. Then you construct a digest info structure, which is a DER encoded ASN.1 structure containing the hash algorithm identifier and the hash value H. The digest info structure follows a specific format. For SHA-256, it's beginning with 0x30 and ending with 0x20 followed by the 32-byte hash. Each hash algorithm has its own digest info prefix. The RFC provides the exact encodings for SHA-1, SHA-256, SHA-384, and SHA-512. Getting this encoding exactly right is critical because any deviation will cause signature verification to fail. After constructing digest info, you then create the padded message structure, EM. This structure consists of 0x00, 0x01, followed by a padding string, PS, of 0xFF bytes. Then, it has another 0x00, followed by the digest info structure itself. The length of PS is calculated so that the total length of EM equals K bytes, where K represents the length of the modulus in octets. The padding string must be at least 8 bytes long, which means the maximum digest info length is K-11 bytes. The deterministic nature of PKCS1 version 1.5 signatures has both advantages and disadvantages. The advantage is that you can verify a signature by recomputing the expected EM and comparing it byte for byte after verification. The disadvantage is that the determinism combined with the simpler padding structure makes it potentially vulnerable to certain attacks, particularly if the implementation has vulnerabilities in the verification process. One important security consideration with PKCS 1 version 1.5 signatures is that the verification process must be constant time and not reveal information through error messages or timing. An attacker who can submit chosen signatures and observe detailed error messages might be able to forge signatures. Modern implementations carefully validate the entire structure, including the padding bytes and algorithm identifier, before accepting a signature as valid. Mask Generation Function MGF1. MGF1 is the mask generation function used throughout RFC 8017 in both OAEP and PSS schemes. Understanding how MGF1 works is important because it is a critical component that provides the security properties of these modern schemes. MGF1 is based on iterating a hash function, and it can generate an arbitrary length output from a seed input. The input to MGF1 is a seed value, which is an octet string of any length, and the desired output length in bytes. The hash function used is a parameter, typically SHA-256 in modern implementations. MGF1 works by repeatedly hashing the seed concatenated with a counter value, incrementing the counter each time, until enough output bytes have been generated. Here is the detailed algorithm. Initialize an empty output string T start with counter C equal to 0. For each iteration, convert C to a 4-byte big endian representation using I2OSP with length 4. Concatenate the seed with this 4-byte counter to form the input to the hash function. Hash this input to produce a hash output of h-len bytes. Append this hash output to T increment C and repeat until the length of T is at least the desired output length. Once you have generated enough output, truncate T to exactly the desired length and return it as the mask. For example, if you want a 256-byte mask using SHA-256 which produces 32-byte outputs, you need to iterate 8 times with counter values 0 through 7. Each iteration produces 32 bytes, giving you 256 bytes total. If you need 250 bytes, you still do 8 iterations to get 256 bytes, then truncate to 250 bytes. The security of MGF1 depends on the underlying hash function being a good pseudorandom function. The iterative structure with the counter ensures that each block of output is derived from a unique hash input. This makes MGF1 suitable for use as a key derivation function and as the masking function in OAEP and PSS. The counter prevents an attacker from finding patterns or correlations in different parts of the mask, which would weaken the encryption or signature scheme. Integer conversion primitives. RFC 8017 defines two fundamental primitives for converting between octet strings and integers. These are I2OSP, which converts an integer to an octet string, and OS2IP, which converts an octet string to an integer. These might seem trivial, but using them correctly is essential for interoperability between different RSA implementations. I2OSP takes a non-negative integer x and a desired output length, x-len, in octets. The integer x must be less than 256 to the power of x-len, which means it must fit in x-len bytes. The conversion produces a big endian representation where the most significant byte comes first. Mathematically, the octet string x consists of bytes x_x-len-1 through x_0, where x_i equals the floor of x divided by 256 to the power of x-len-1 - i, all modulo 256. In simpler terms, I2OSP is just big endian byte encoding. You extract bytes from the integer starting with the most significant byte. For example, the integer 258, which is 0x0102 in hex, when converted with length 2, produces the octet string 0x010x02. If you try to convert an integer that's too large for the specified length, I2OSP must fail with an integer too large error. OS2IP performs the inverse operation. It takes an octet string, x, of length xlen, and converts it to a non-negative integer, x. The conversion treats the octet string as a big Indian integer. Mathematically, x equals the sum, from I equals 1 to xlen, of x at position xlen minus I, multiplied by 256 to the power of I minus 1. In other words, each byte contributes to the integer based on its position, with the first byte being the most significant. For example, the octet string beginning with 0x and ending with 02 converts to the integer 256 times 1, plus 1 times 2, which equals 258. The octet string beginning with 0x and ending with FF converts to 255. Leading 0 bytes are perfectly valid and represent high-order 0 bits of the integer. OS2IP never fails because any octet string can be interpreted as an integer. These primitives are used throughout the RSA operations. When you encrypt, you convert your padded message EM to an integer M using OS2IP. Perform modular exponentiation to get C. Then convert C back to a ciphertext C using I2OSP. The same pattern applies to decryption, signing, and verification. Using Big Endian encoding ensures that different implementations can exchange encrypted messages and signatures successfully. RSA key generation process. Generating secure RSA keys is a critical operation that must be done correctly to ensure the long-term security of the cryptographic system. RFC 8017 provides detailed guidance on the key generation process, including requirements for the prime numbers and recommendations for key sizes. Step 1 is to determine the key length. The modulus n should be at least 2048 bits for security through 2030. For higher security or longer lifetimes, use 3072 or 4096 bits. The key length determines the security level but also affects performance. Longer keys provide more security but make encryption, decryption, and signature operations slower. You need to balance security requirements against performance needs for your application. Step 2 is to select the public exponent E. The most common choice is 65,537, which is 2 to the power 16 plus 1. This value is popular because it has only 2 bits set in its binary representation, beginning with 0x01, ending with 01, making exponentiation fast during encryption and signature verification. The public exponent must be odd and greater than 2. Some systems use the smaller value 3 for even faster operations, but this requires careful padding to avoid security issues. Step 3 is generating the prime factors. Generate 2 distinct random prime numbers P and Q, each of approximately half the bit length of n. For a 2048-bit key, both P and Q should be around 1024 bits. The primes must be generated using a cryptographically secure random number generator and must be strong primes, meaning P-1 and Q-1 should have large prime factors to resist certain factorization attacks. Step 4 computes the modulus n by multiplying P and Q. Verify that n is exactly the desired bit length. If not, you need to generate new primes. Also verify that P and Q are sufficiently different. If P and Q are too close, Fermat factorization can find them efficiently. A good rule of thumb is that the absolute difference between P and Q should be at least 2 to the power of n len, divided by 2, minus 100, where n len is the bit length of n. Step 5 computes the private exponent d. First calculate phi of n, which equals P minus 1 times Q minus 1. Then compute d as the modular multiplicative inverse of E modulo phi of n. This means d times E is congruent to 1 modulo phi of n. The extended Euclidean algorithm efficiently computes this inverse. Finally, compute the CRT optimization values. dp equals d mod p minus 1, dq equals d mod q minus 1, and q inverse equals the inverse of q mod page. These values dramatically speed up private key operations and should be stored with the private key. Security considerations and key sizes. Choosing the right RSA key size is crucial for security. The security of RSA depends on the difficulty of factoring the modulus n. As computers get faster and factoring algorithms improve, we need to use larger keys to maintain security. RFC 8017 provides guidance, but security recommendations are updated over time based on current computational capabilities. As of 2024, 2048-bit RSA keys are considered the minimum for most applications. NIST and other standards bodies recommend 2048 bits for security through 2030. This provides roughly 112 bits of security, which means that an attacker would need approximately 2 to the power 112 operations to factor the key. This is currently infeasible even with massive computational resources and will remain so for the foreseeable future with classical computers. For applications requiring longer-term security or protecting highly sensitive data, 3072-bit or 4096-bit keys are recommended. A 3072-bit key provides approximately 128 bits of security, comparable to AES-128. A 4096-bit key provides even more security margin. However, these larger keys come with performance costs. A 4096-bit RSA operation is roughly 7 to 8 times slower than a 2048-bit operation due to the increased computational complexity of modular exponentiation with larger numbers. The quantum computing threat is an important consideration for long-term security planning. Large-scale quantum computers running Shor's algorithm could factor RSA keys efficiently, breaking RSA encryption and signatures regardless of key size. While such quantum computers don't exist yet, organizations protecting data that must remain secure for decades should consider quantum-resistant algorithms like lattice-based cryptography or hash-based signatures. Another critical security consideration is the quality of random number generation. The primes P and Q, the OAEP seed, and the PSS salt must all be generated using a cryptographically secure random number generator. If an attacker can predict or influence these random values, they can compromise the entire system. Use operating system provided CSPRNGs like /dev/urandom on Linux or cryptgen random on Windows, or hardware random number generators when available. Implementation vulnerabilities are often more dangerous than theoretical attacks on the mathematics. Timing attacks can leak information about private keys through variations in execution time. Power analysis and electromagnetic analysis can extract keys from hardware implementations. Side-channel attacks have successfully extracted RSA keys from smartphones, smart cards, and servers. Constant time implementations and proper countermeasures are essential for real-world security. Comparison of encryption schemes. RFC 8017 defines two encryption schemes, RSAES-OAEP and RSAES-PKCS 1B15. Understanding the differences between these schemes helps you make informed decisions about which to use for your applications and when you might need to support both for compatibility. RSAES-OAEP is the modern, recommended encryption scheme. It uses optimal asymmetric encryption padding, which is designed with provable security properties. OAEP provides semantic security. This means encrypting the same message twice produces different ciphertexts because of the random seed. This prevents attackers from recognizing patterns even if they know the plaintext. OAEP is also secure against adaptive chosen ciphertext attacks, where an attacker can obtain decryptions of chosen ciphertexts and try to use that information to attack a target ciphertext. The padding in OAEP is more complex, involving 2 rounds of masking with MGF1. This complexity provides security benefits, but it also makes implementation slightly more complex. The maximum message length for OAEP is smaller than PKCS 1B 1.5. It is K-2H len-2 bytes, compared to K-11 bytes. For a 2048-bit key with SHA-256, OAEP can encrypt at most 190 bytes, while PKCS 1B 1.5 can encrypt 245 bytes. RSAES-PKCS 1 version 1.5 is the legacy encryption scheme that has been in use since the 1990s. It uses simpler padding consisting of 0x00, 0x02, random non-zero bytes, 0x00, then the message. This simplicity is actually a weakness from a security perspective. PKCS 1 version 1.5 is vulnerable to adaptive chosen ciphertext attacks, particularly the Bleikenbacher attack, where an attacker who can determine whether a ciphertext has valid padding can gradually decrypt messages or even recover the private key. Despite its vulnerabilities, PKCS 1 version 1.5 remains widely deployed for backward compatibility. It is used in TLS 1.2 and earlier versions, in many email encryption systems, and in legacy applications. Modern implementations include careful countermeasures against known attacks, for example, constant time padding validation, and never revealing whether padding validation succeeded through error messages or timing. For new applications, always use RSAES-OAEP unless you have specific compatibility requirements that mandate PKCS 1 version 1.5. If you must support PKCS 1 version 1.5, ensure your implementation includes protections against known attacks. Even better, consider whether you really need RSA encryption at all. For most applications, a hybrid approach where you use elliptic curve Diffie-Hellman for key exchange and AES-GCM for bulk encryption provides better performance and security than RSA-based encryption. Comparison of signature schemes. RFC 8017 also defines two signature schemes, RSASSA-PSS and RSASSA-PKCS 1 version 1.5. Similar to encryption, understanding these differences helps you choose the right scheme and implement it securely. RSASSA-PSS is the modern probabilistic signature scheme. It uses a random salt in each signature, making the scheme probabilistic. This means signing the same message multiple times produces different signatures. The randomization provides security benefits, including resistance to certain forgery attacks. PSS uses EMSA-PSS encoding with masking operations similar to OAEP, providing provable security guarantees. The salt length in PSS is configurable, but typically set to the hash output length. Longer salts provide more security but make signatures slightly larger. The salt is recovered during verification, so the verifier doesn't need to know the salt value beforehand. This makes PSS flexible while maintaining strong security. PSS is particularly well suited for modern applications and is required by some security standards for high-assurance systems. RSASSA-PKCS 1 version 1.5 is the deterministic signature scheme that has been standard for decades. It uses EMSA-PKCS 1 version 1.5 encoding, which includes a digest info structure containing the hash algorithm identifier and message hash. Being deterministic means that the same message and key always produce the same signature. This can be useful for applications that need signature stability or want to verify signatures by comparison. The security of PKCS 1 version 1.5 signatures depends critically on correct implementation. The digest info structure must be encoded exactly according to the standard. The padding bytes must be validated during verification. Any shortcuts or mistakes in implementation can lead to signature forgery vulnerabilities. Despite these concerns, PKCS 1 version 1.5 signatures are still widely used and are generally considered secure when implemented correctly. In practice, both signature schemes are acceptable for most applications when implemented properly. PKCS 1b1.5 has the advantage of being deterministic, which some applications prefer. PSS has stronger security proofs and is preferred for new cryptographic protocols. For maximum compatibility, you might need to support both schemes. Many TLS implementations, certificate authorities, and cryptographic libraries support both PSS and PKCS 1b1.5 signatures. Hash function selection. RFC 8017 is hash function agnostic, meaning you can use it with various hash functions. However, the choice of hash function significantly impacts the security of your RSA operations. Let's discuss how to select appropriate hash functions for different use cases. SHA-256 is the recommended choice for most applications today. It provides 256 bits of hash output and has 128-bit collision resistance, which is more than adequate for RSA with 2048-bit or even 4096-bit keys. SHA-256 is fast on modern processors, widely supported in cryptographic libraries, and has no known practical attacks. Unless you have specific requirements for a different hash function, SHA-256 is a solid default choice. For applications using 3072-bit or 4096-bit RSA keys for long-term security, SHA-384 or SHA-512 might be more appropriate. These provide larger hash outputs and higher collision resistance, better matching the security level of the larger keys. SHA-512 is actually faster than SHA-256 on 64-bit processors due to its use of 64-bit operations. However, the larger hash outputs increase the size of signatures and reduce the maximum message size for encryption. SHA-1 should be avoided for new applications. While RFC 8017 includes SHA-1 for backwards compatibility, practical collision attacks against SHA-1 have been demonstrated. Using SHA-1 for signatures could allow attackers to create different messages with the same signature. Some older systems still require SHA-1 for compatibility, but you should plan to migrate away from it. The hash function choice affects several parameters in RSA operations. For OAEP encryption, the hash length determines the maximum message size. For PSS signatures, the hash length typically determines the salt length. For PKCS 1b1.5 operations, the hash function determines the digest info encoding. You must use the same hash function for signing and verification, and for encryption and decryption, otherwise operations will fail. An important security principle is that the hash function should have security comparable to the RSA key. Using SHA-256 with a 2048-bit key provides balanced security where both components offer approximately 112 to 128 bits of security. Using a weak hash function with a strong key wastes the key's security potential. Conversely, using a very strong hash function with a weak key doesn't improve overall security since the key becomes the weak link. Implementation best practices. Implementing RSA cryptography correctly is challenging. Many subtle details can lead to vulnerabilities if not handled properly. Let's cover the most important best practices that every RSA implementation must follow to be secure. First, use established cryptographic libraries rather than implementing RSA from scratch. Libraries like OpenSSL, BoringSSL, LibreSSL, and platform-specific crypto APIs have been extensively reviewed and tested. They include protections against timing attacks, proper random number generation, and correct implementation of the RFC 8017 specifications. Rolling your own cryptography is strongly discouraged unless you have deep expertise and resources for security review. Second, implement constant time operations for all private key operations. Decryption and signing must take the same amount of time regardless of the input data or key values. Variable timing can leak information about the private key through timing attacks. Use constant time modular exponentiation algorithms. Avoid conditional branches based on secret data. Pad operations to fixed time durations if necessary. This is especially critical for systems exposed to potential timing attacks, which includes any networked service. Third, validate all inputs thoroughly before processing them. Check that ciphertext and signature values are in the valid range 0 to n-1. Verify padding structures completely before accepting them as valid. Return generic error messages that don't reveal which specific check failed. Never expose detailed error information that could help an attacker craft specific attacks. Fourth, use secure random number generation for all random values, including OAEP seeds, PSS salts, and most critically, the prime numbers P and Q during key generation. Use operating system CSP RNGs or hardware RNGs. Never use language standard library random functions, which are not cryptographically secure. Test random number generator quality, and ensure it has sufficient entropy before generating keys. Fifth, protect private keys carefully. Store them encrypted when at rest, using strong encryption and key derivation functions. Use hardware security modules or trusted execution environments for high security applications. Implement proper key lifecycle management including generation, storage, rotation, and destruction. Zeroize memory containing private key material after use. Consider using key storage mechanisms that prevent extraction such as TPMs or secure enclaves. Common attacks and vulnerabilities. Understanding common attacks against RSA helps you implement secure systems and avoid known pitfalls. While RSA is mathematically sound, implementation mistakes and protocol issues have led to numerous vulnerabilities over the years. The Bleikenbacher attack targets PKCS 1 version 1.5 encryption. Discovered in 1998, this adaptive chosen ciphertext attack exploits the padding validation during decryption. By submitting many crafted ciphertexts and observing whether decryption succeeds or fails, an attacker can gradually decrypt a message or even recover the private key. The attack works because implementations reveal through timing or error messages whether the padding is correctly formatted. Modern defenses include constant time validation and carefully designed error handling. Timing attacks analyze variations in execution time to extract secret information. Different code paths for different values, or operations that take different times based on input, can leak information. For example, if modular exponentiation is faster when certain bits are 0, an attacker can measure timing to determine private key bits. Defenses include constant time algorithms, blinding techniques, and ensuring all code paths take equal time regardless of secret values. Small public exponent attacks happen when the exponent e equals 3, and messages are small enough that m cubed is less than n. The resulting ciphertext c then equals m cubed without any modular reduction. This allows for trivial decryption by simply taking the cube root. This is why proper padding is essential, and it's also why OAEP and PKCS 1 version 1.5 both include padding. This padding ensures that the encrypted value is close to n in magnitude. Common modulus attacks happen when the same modulus n is used with different key pairs. If two users share the same n with relatively prime exponents e1 and e2, an attacker who sees the same message encrypted to both users can recover the message without any private keys. Never reuse moduli between different key pairs. Padding oracle attacks are generalizations of Bleikenbacher's attack. Any mechanism that reveals information about whether padding is valid creates a padding oracle. This includes error messages, timing differences, or even power consumption patterns. Defenses must ensure that all error cases are indistinguishable to the attacker through any side channel. RSA in practice and real-world applications. RSA is ubiquitous in modern cryptographic systems. Understanding how RSA is used in practice helps you apply RFC 8017 correctly in your own applications and understand the security properties of systems you interact with daily. In TLS and HTTPS, RSA plays multiple roles. RSA certificates contain public keys that identify servers. These certificates are signed using RSASSA-PKCS 1 version 1.5 or RSASSA-PSS by certificate authorities. During the TLS handshake, RSA can be used for key exchange where the client encrypts a pre-master secret with the server's public key, though modern TLS 1.3 prefers elliptic curve Diffie-Hellman instead for forward secrecy. SSH uses RSA for authentication. When you connect to a server with SSH, the server proves its identity using an RSA signature on the session data. User authentication can also use RSA keys where the client proves ownership of the private key by signing a challenge. SSH typically uses RSA with SHA-256 or SHA-512, and 2048-bit or 4096-bit keys are common. Email encryption with PGP and S/MIME often uses RSA. A message is encrypted with a symmetric key, then that key is encrypted with the recipient's RSA public key using RSAES-PKCS 1B1.5 or RSAES-OAEP. Digital signatures on emails use RSA to prove authenticity and integrity. This allows you to send encrypted email that only the intended recipient can read and to verify that emails genuinely came from the claimed sender. Code signing uses RSA signatures to verify the authenticity of software. Operating systems, mobile apps, and software updates are signed with RSA private keys held by developers or organizations. Your device verifies these signatures before installing or running code. This prevents malware from impersonating legitimate software. Code signing typically uses RSASSA-PKCS 1B15 with large key sizes and SHA-256 or stronger hash functions. While RSA remains widely used, there is a gradual shift toward elliptic curve cryptography for new applications. ECC provides equivalent security with much smaller keys. A 256-bit ECC key provides similar security to a 3072-bit RSA key. ECC operations are faster and use less bandwidth. However, RSA's mathematical simplicity, longer track record, and existing deployment ensure it will remain important for many years. Understanding RFC 8017 remains essential for anyone working with cryptographic systems. Conclusion and future directions. We've covered RFC 8017 comprehensively, from the basic RSA primitives through the modern OAEP and PSS schemes to implementation best practices and real-world applications. RFC 8017 represents decades of cryptographic research and refinement of the RSA system into a well-specified, secure standard. The key takeaways are to prefer RSAES-OAEP for encryption over RSAES-PKCS 1 version 1.5 whenever possible. This is because OAEP provides stronger security guarantees. For signatures, RSASSA-PSS offers provable security benefits. While RSASSA-PKCS 1 version 1.5 remains acceptable, it must be properly implemented. Always use key sizes of at least 2048 bits, and preferably 3072 or 4096 bits, for long-term security. Use SHA-256 or stronger hash functions. Never use SHA-1 for new applications. Implementation security is paramount. Use established cryptographic libraries. Implement constant time operations for private key processing. Validate all inputs completely. Use high-quality random number generation, and protect private keys carefully. Many RSA vulnerabilities come not from the mathematics but from implementation mistakes, side channels, and protocol issues. Looking forward, the cryptographic landscape is evolving. Post-quantum cryptography is becoming increasingly important as quantum computers advance. NIST has selected several post-quantum algorithms including Crystal's Kyber for encryption and Crystal's dilithium for signatures. These will eventually supplement or replace RSA in applications requiring long-term security against quantum threats. However, RSA's practical importance won't disappear soon. The massive existing deployment of RSA in certificates, keys, and protocols means it will remain relevant for decades. Understanding RSA through RFC 8017 provides foundational knowledge applicable to both current systems and future cryptographic protocols. The principles of padding, secure key generation, and careful implementation apply broadly across cryptographic systems. Thank you for your attendance. Please consider subscribing to the channel.